Yeah, well, thank you for having us here. Thank you, Christian, for the kind introduction. Thank you all for coming here tonight. Is the micro on? Yeah. Sorry. Okay, so let's get started. We're talking today about our project VE.io, and this is a solution for microservice orchestration that we are developing at our company Communda in Berlin. And to get started, let's go back to the basics. Microservice is a solution or an architectural pattern to build large software systems. If we go back a couple of years when this trend gained traction, then it was more or less introduced by tech companies like Amazon and Netflix, who have been building very large applications and use this pattern to manage the complexity of these applications. So you decompose your applications into modules that encapsulate certain functionality. These modules have, thanks to the service idea, a very clear interface, and then you can assign this developing the task of developing and operating these services to individual teams in your organization, and this then allows you to manage this overall software development process and to also scale it up to a lot of people. And this is very nice if we look at the individual services, but often you have requirements that span the functionality of many services that require that some function or some services interact in a way that is predefined in order to generate some kind of business value, something that makes our customers happy. And this poses a challenge to the microservice idea in the sense that it introduces at least some kind of coupling between the services. Somehow we have to interact. And of course, we don't want to lose all the benefits the microservice architecture gives us. Instead, what we want is a solution that orchestrates or combines the services such that the individual parts they contribute to the solution results in something that is a meaningful whole. So unlike this, where we have two parts that are kind of the solution but do not really match up, we want to keep the benefits of having a microservice architecture, so you don't want to throw away the loose coupling between services, for example. And we also want to expand these benefits of having this kind of approach to the orchestration and coordination part. And this means that we want to have a very clear model how to develop the coordination of services. We want to have, for the operations at runtime of running services and the orchestration, we want to have a way to scale orchestration and to have a resilient and robust way to do orchestration. And lastly, we want to have visibility for basically all the stakeholders that are involved in the process. So developers want to know what's going on at runtime to evolve their systems. Operations want to know if at runtime you have errors and probably want to fix them. And lastly, the business wants to know what's going on in the overall distributed system to get an insight how well their business goals are fulfilled. And so this is the problem statement that we're looking at today, and probably have a solution for that.
Yeah, so there is different ways to tackle this, and there's one way that we are focusing on today. It's an opinionated way. It's orchestration and workflow. And this is something that has been around for many years. It's not a new principle. We will talk about a new system to implement this today. But what is this about for those who are not very familiar with it? So orchestration workflow, first of all, is a way to design interactions between loosely coupled components, and this allows you to do some certain things. Like, for example, here, those who can see this from the back, we receive some event or message, and then this interaction starts. Then there can be different steps that are performed in this case, in a sequence. Here, there is like a decision, so either we go this way or we go that way, and we can have things like waiting for timeouts. We can wait for intermediate events from different systems to occur, and then we can continue. And basically behind this you have, I'm not going into detail here, but behind this you have a lot of patterns that have emerged in enterprise integration. Like this is orchestration, this is state machine, this is also compensation and the saga pattern behind it. So workflow is a unification of those different things that allow us to orchestrate work and to distribute work in distributed systems. This is both, in the workflow automation system, this is both source code and documentation. So if I draw this, then I can give it to the system and it can execute it directly. So it's not like, okay, we draw this, we print it out, and then somebody has to program everything that we see, but it's kind of living, running documentation, which is very nice to have. Then the workflow systems that can then run this give you an answer to the problem of how to run this, how to scale this, and how to be resilient. We're going to see how the CB system that we're going to present later does that. And as Thorben mentioned, during the life cycle of our orchestration, we get, in different phases, we get a lot of visibility into the system. So at design time, we see what is going on. At runtime, we can have errors on these different steps. We're going to see that in action. And then also a business stakeholder can look at this and then see how effective this is, where is time being spent, how long do they step take on average, and so on and so forth. Now, what we are going to present today is a new open source system that we have developed with our company Calcutta. We are from Berlin, and this is an open source microservice orchestration and workflow engine. We have launched this in August. It's kind of in a very, very early stage right now. At Calcutta we have a very different product in the market that is very mature and used by different companies, but this one is very early stage, and Thorben and myself were working on this product since over a year ago. And what we do here is we rethink workflow based on microservice principles. So we're going to see how CB gives you a lot of loose coupling between the components in there by applying publish-subscribe protocols for orchestration. CB is also very lightweight and composable, so CB doesn't do a lot. It only does this execution of workflow, and that's it. So if you want to build other systems that build on top of it, like a system that calculates the average duration of certain steps in the workflow, so you can subscribe to stream of events and you need to build those systems yourself. So it is very small and it solves this specific problem, but not all problems. And this is very different from heavyweight systems that we've seen in the past, particularly in the workflow and then also BPMN, business process management space. And we came up with this ambition to sort of push the boundaries of what is possible with workflow. So we're going to show how the CB system is on this machine that we see there more than 100 times faster than traditional workflow engines. And we're going to explain how it is horizontally scalable and how it is fault tolerant, not in the traditional way where I have redundant hardware on which a database runs, but more in a modern way where I have cloud architecture where data is replicated across different nodes and machines to achieve the fault tolerance. So that's the menu. Thorben is going to give us the outline of the talk.
Yep. Today, so we're giving an overview of CB, so the general principles, how it works. We are going to look in particular into how it achieves resilient service orchestration, so how it behaves in the presence of failures in the overall system. We will have a look at performance and compare it to traditional workflow systems and Apache Kafka probably. And we will look at to the introspection aspect, so how can we track the progress of workflows in this distributed system. And then we'll have a Q&A. Basically, all of these steps will be accompanied by some live hacking and really showing how the system works.
Yes. Christian, when do we need to shut up? When is the...
Yes, no, the definitive end of the session, I believe an hour is
okay, we should
a good
go for an
benchmark,
hour.
but if you have interesting stories to tell or interesting things to show us, I believe...
At some point people are going to leave. Yeah. All right, so let's get this started. If you want to get CB, you can go to the website, cb.io, you take into the download page, it's on GitHub. There's been a new release today by our team. You can download that and use it. I'm going to show this on my computer. So I have already downloaded the ZB distribution, and I'm going to extract it. I already have extracted it. Very good. And basically, for those who can see this, this is just, you know, there's a bin folder, a configuration folder, some libraries, and a folder for log files. This system is written in Java, so if you go into library, you see there's a bunch of Java files in there. Who here in the room is a Java developer? Like half the people? Golang developers? 2? We'll have some Golang code, right? And I guess everybody else is more like C# or and then JavaScript. Yeah, okay, cool. So it's Java, and then the other half is diverse. Nice. So go into the bin folder here, and basically I can start it by saying broker. So this is a client-server architecture, the ZB system, and well, this doesn't tell us a lot, but it's there, it's running, and this is the server. We call it a broker because it doesn't really do a lot of stuff. It basically distributes work to different microservices that can then subscribe to it. So that's why we call it a broker, and it has a client-server architecture. And what we can see right here now is that for those who can see this far, we are now listening on a particular port for incoming connections. So that's the first step. System is there. Now, as we mentioned before, it is a orchestration and workflow engine, and it uses BPMN for workflows. Who has heard about BPMN? Almost everybody. Who likes BPMN? Bernd, you're not allowed to raise your hand. All right. So BPMN, for those who don't know it, is a standardized language for defining workflows. And they can be small, they can be complex, and everything in between. And as we said in the beginning, there's lots of different things that we can do. We can have decision paths in the process. We can have parallelize things. We can, so like this idea of the fork join concurrency, this idea of compensation. So there's a lot of things that you can do with it. The most important part of it is that, as I said before, it's source code, it's directly executable. And at the same time, it's documentation, so we see what is going on. Now, for today's demo, we have prepared a very, very simple BPMN process. So it looks like this. Basically, I can upload a photo, I can watermark the photo, I can create a thumbnail of the photo, and that's it. And we will have 2 services connecting to it. One is able to do watermarking, and the other one is able to do thumbnailing. This one is implemented in Java, this one is implemented in Go. And the first thing we need to do is we can deploy this workflow. And for that, we will use the ZB command line. So there is a nifty small tool that's called CBCTL. And if you run it, it gives you a little bit of help. And you see that you can say CBCTL create, I don't know, code completion, create workflow. And then I'm down here. And then I give it the name of the, like this case it's called process.bpmn. And maybe I can scroll, no I can't. But I'm going to take it to the top. So we type CBCTL. Since we're just connecting to the default localhost running browser with the default port, I didn't have to say go to that IP address or go to that host. And then I'm just deploying this, and now it answers, okay, deployment created, so this workflow is not known. There is a small application that you can use, Java-jar target, and then it is called ZB Simple Monitor. And when we run this, this is a Spring Boot application. So this is an example of, I said before that ZB is very small, so this broker does not have a user interface. It's just this middleware component running there. But somebody sitting there in the back has written this Java application that you can use to then look into the system and see what is going on. So right here, we go in there, we can add the broker, and now I could go in here. I see that this workflow here is available and has been deployed. There's an alternative to the BPMN in CB. So if you have very small things, like for example, this workflow only had 2 tasks. I could have done this with a simple YAML file. So CB also understands workflows that you describe in YAML. So for example, here it says the name of the workflow, and then I have 2 tasks. This is called collect money, and this one is called fetch items. This has 3 retries, and this one as well. So with the simple YAML file, I can also write up those workflows. Of course, if I have 20 steps and more complex routing logic between them, then this is going to be really hard to deal with, and then I would go for a more like graphical way of representing it. All right, now we said that we wanted to connect these microservices to give some work to them, and Thorben is later going to go into the details, but there is a publish subscribe protocol between the broker who runs the workflow and then the services that subscribe to those tasks in the workflow. And what I'm now going to do is I'm going to write up the first step in Java so that you'll get a feeling of how to program with the system. And I think Thorben wanted to explain a little bit what I'm doing. So let's try this.
Yeah, so this is Eclipse for everyone who doesn't know Java IDEs. And it's basically a pretty much empty project in Eclipse, and now we're creating a class that we will use to run our worker that does the watermarking.
So this would be our microservice.
Yeah. So now Daniel is going to instantiate the CB Client. This is a Java library that you can embed into your application, into your worker, and that you can use to connect to the CB broker.
This is harder when people are...
So it's called CB Client, and there we have it. And this CB Client API gives you basically access to all the operations that CB exposes to client applications. Yeah, we can tell it to which broker we want to connect. Or which, actually, if we have a cluster of brokers, it can connect to all the brokers, but we have to give it an initial contact point, so the very first broker.
Is this correct, Tom?
It's 51015. Yeah.
So I wouldn't have needed to put this, but we wanted to show that this is how you specify it.
And now we can start writing the code that subscribes to the CB broker for tasks of the type watermarking, for which the entry point is the tasks client. So now we open the subscriptions to all tasks that are created on the topic. The default topic is the one that is running in the CB, or is already created in the CB broker, and that we have deployed our workflow model to. And we have to define the task type, so we can have different handler implementations for different types. Type is then also specified in the BPMN model here, so that's the way how the handlers in the end linked to the model. This is now the actual logic of the handler implementation, so we give it an implementation in which basically a callback that is invoked with every task of this type that we receive from the subscription. And we have to add 2 more parameters about locking of tasks. We'll get back to that later. And that's it. And with the open call, the client actually connects to the broker, subscribes to the tasks, and from that point on, the client application receives any tasks that are created in the ZB broker, and the handler gets involved.
This would need to be done better, but all right. So in here, there's the actual business logic. So we've opened the subscription, and as Tom said, in here there's the actual business logic. And so what we see here is we're implementing a task handler interface, which is a functional interface. We could also have used the Lambda function, and this is out of the ZB Client package. So basically here, we get a callback whenever on the broker side we go into this particular step here. So whenever we reach this particular step, we're going to get a callback here. So this handle method is going to get called if we are currently subscribed. And then in this method, we can now get access to the payload. So this is what we're doing here. Payload is JSON. We're going to talk about it a little bit more later. So we're going to inspect the payload, then we do a bunch of stuff that we can ignore for the moment. This is about watermarking, not about ZB. And then we see client complete with some output payload and execute. So now we are done, and we're marking the task to be completed, and then on the broker side it can continue to the next one. So let's do that. What we first do is we start an instance of this. And there is a little UI to our demo application that has been written. This is also written in Go. And it looks like that. Also very to the, so yeah, then I think I have it here. And now here you can upload a picture of a horse. So what we see right here, of course I have rehearsed before, so let's ignore those guys and let's focus on this one. So we have uploaded this picture. Who knows this guy? Yeah? Bojack Horseman. Yeah. And so he's all here, he's alive, he's shaking his, I don't know what this is called in English, this part of the horse. But you know he's there. And he's basically very, very happy. If we go, Bojack is never happy, but if we go to workflow, to the monitor here, we see that basically we have started a new instance. And I mean, it has completed the start event, yes, but it's not waiting here because I have successfully written this Java service, but we haven't really started it yet. So the subscription is open, and then now we're waiting here until the subscription is open. And now we can try to do that. So let's start this guy. All right, and you see that now it picks up this task, it prints out some stuff here. And let's first go here. So if we refresh, we see that horse 2 has been watermarked. No more shaking of the hair, but nice little ZB logo on the bottom. So this is basically what our service has done. And when we refresh here, then we see that now this step has also been completed, and we are now waiting here, and we haven't started that service yet. So let's go to this service as well. And that one is also, and now this one is written in Go. I'm just going to start it, and it's going to do its work. And then when we go back here, we hopefully should see that, yes, now the full workflow is completed. And, oops, wrong, lost in tabs. Now here we have also the thumbnails, so it's smaller. And if you are like for the Go developers here in the room, just to I'm not going to write this because I couldn't, but just going to show you this. So how do you use this? You go for your ZB client. So it's called CBC Go, ZB Client Go, and then it's very similar to the Java one. So we say new client, and then we have it here, and then we, like this is processing the post request of the upload, and then we can see down here that we are saying CB Client.new workflow instance, and this is basically then kicking off the workflow, so this is starting the workflow, and then this is the thumbnail service, again importing the CB Client, also then instantiating the client here, connecting to my local broker. Then I have, in this case, this is the subscription variant that is done in Go, so we create a task consumer. Again, on the default topic, here the task type is thumbnail, and then we basically get, from this we get a channel. So in Go there's this concept of channels, and channels connect, for example, between different Go routines. So Go routines are like loosely coupled actors that run inside a Go program, and they can communicate through channels. This is, if you're from the Java world, it's a little bit like Akka, or maybe to a certain degree Vertex. And so I have a channel, and on this channel I will now receive tasks. So as the broker goes into this step in the workflow, I will receive a task on the channel. So we have 4, and then select on the subscription channel, and then whenever we get a task, we get a message here, and then again it gets processed. I'm not going to go into those details, but then in the end it's going to complete it, and that's it. So that's the Go part. Now going back here. So you've looked a little bit into how I can connect my services. The data flow. So a workflow, so this is a workflow. Whenever we execute it, we call that a workflow instance, so particularly run through this. And then we have payload, so that I can give some initial data inside, and then the first task can work on this data, and it can change it, can output it again, and then it's going to go into the next step, and so on and so forth. If you have parallelism, which CB cannot do yet, but if it could, then basically on each branch, you would have 2 copies of this document, and then they get merged at the merge point when the flows are joined. So we can observe this a little bit if we go into the monitor here, and I mean the UI is just beautiful, but you can that didn't really help. No. You can sort of see it up here. So this is the JSON. This is a JSON object or JSON document, and basically what's relevant to our application is the watermark path and the image path, which are local paths on my file system, but this could be anything. Then you can work with this inside the different steps, marshal it, unmarshal it, and then everybody can communicate through JSON. We decided on JSON because with the ZB project, we want to address different programming languages, and most programming languages, maybe except Java, have very good support for JSON, and some programming languages even native support for JSON, and this is quite popular at the moment, and we thought it would be good to go with the JSON. Internally, if you're interested, this system needs to be really fast and really performant and really efficient. We talk about that later a little bit. Internally, it is actually not JSON, it's binary JSON encoded as a message pack. Nobody heard of that, I guess. But this allows you to work with it on the binary level. So you don't need to parse it inside the ZB all the time, but you can work with it on the binary level. All right, so ClientServer, on the server side, I usually have a cluster. On this machine, I now have only 1 broker, but usually I have a cluster. And then with the client, you have initial contact points, you connect to one of the nodes that you know in the cluster, and that is going to tell you about the other nodes that are in there. How does it work internally? Let's go there a little bit. ZB interprets workflow execution as stream processing. So inside ZB, whenever something happens, so when we start a workflow instance, when it executes a certain step, when it goes to the next step, when it pushes out a task to one of the subscribers, when the subscribers signal back that the task is completed, all of those things are either commands or events. So if I want something to happen, then it's a command. If it happened, that's the outcome of this action, then it's an event. And this is all it does internally. So the system internally has this log of everything, like all the commands and all the events that have happened inside the system. And so it's stream processing or event sourcing, all of those terms are currently flying around in our space, but you can think about it as a system like that. To give you a more concrete idea, I'm going to show you this stream, and you can subscribe to that from the outside, because it may be really interesting to get those events and do something with them. I'm going to go into those examples more later, but basically you see everything that's going on, so you can do interesting calculations. You can archive them somewhere to have a complete audit log of everything that happened, and so on and so forth. So I'm going to write some code again and show you how you can consume this stream, subscribe to it and consume it.
Yeah, so a new class for a new application. It is again a Java application that is executable, and it uses again CBC Client as the entry point to the API. From there now we can create a different type of subscription. So this time it's not a task subscription, but a subscription, an event subscription to a topic. And
this is the topic name now?
Yeah, there we define the topic name, to which we subscribe, similar to what we saw with the task subscriptions. Then we have a couple of parameters that we can define. The most important one is the event handler, which start, I think it's .handler.
It's the handler, yes.
And in contrast to the task subscriptions, this is now a handler that consumes or reacts to any kind of event that the ZB broker produces, not just tasks that need to be done, but basically any kind of workflow-related data or event.
So here we're just going to print it.
And an event basically consists of two parts. It has metadata, which is common to all events, and, for example, identifies the position in the audit log of ZB. And it has some payload that is then specific and identifying what the event actually stands for in the stream. So here we are using the metadata to log the position of every event. This is then unique for each event. Each event has a type that we can log. So for example, tasks are an event type, everything that is related to a task. And then we will log the payload of the event.
The JSON here, right?
Yeah, exactly. This is now not the payload of the task handler that we saw before, but the event itself represented as JSON. We will see this when we run this in a second, how this looks like.
Okay. And then I need to configure this a little bit in addition, right?
Yeah, exactly. So we can tell at which, or we can define at which point in the log stream of events we want to start. And here we say that we want to always begin at the very start of the stream. We also have to give it a name for the subscription, because we can have multiple subscriptions, and the broker also keeps track of which events have been consumed by a subscription already. So this is how we identify to which subscription this handler belongs.
Yeah.
some boilerplate cleanup. So now we can run this, and this basically logs now all the events that have been ingested and also handled and produced by the ZB broker. And there we see the different kind of types of events. So in the beginning, the deployment, which corresponds to the BPMN file that we have uploaded. Then we have workflow instance events for when we uploaded the photo via the UI. This starts a workflow instance in ZB. We have events of type task, which then corresponds to publish or to the events that get published to the task handler. The handler then calls back and completes the task, which again triggers some changes in the workflow instance and makes the ZB broker produce new events of the workflow instance type. And ultimately, the workflow instance will become completed. And yeah, that's about it. And for every event, we have some kind of data that can be used to introspect how the workflow instance is processed.
What we can also see here is that what I said before is this alternation of commands and events. So, for example, first example is here. We created the deployment, so we have a create deployment. This is a command, so create this deployment. And then this was successful, so we have an event that says deployment created. We have the same pattern here. So we see that workflow instance, that's when we start the workflow, we have the command create workflow instance, and this is then answered by workflow instance created. Those commands here, they get sent from the client to the server, and then the server internally, based on the state that it has, will process those commands and try to apply it to its internal state machines. If they're valid, then they can be applied, and then it succeeds. If they're not valid, based on the internal state and state machines, they get rejected. Thorben is going to go more into the details around the state machines and so on later. Then we're going to revisit those events here. Like, for example, the task gets created, like the create command, created, logged, completed. So we're going to understand that in a few minutes. So I can subscribe to all those events here. The same is actually what this application is doing. So this is nothing else than an application that subscribes to all those events, and internally it has a database, and it just materializes some calculated state based on those events inside this database. So for example here, we now see that for this workflow instance, something like this is a state, this step is completed and so on. And this is then materialized inside this database. You could redo it. So we saw that in the example here. I said start at the head of the topic. So start at the beginning of history, so to say. This is, if you are familiar with the Apache Kafka system, then you would be familiar with this. So here we start at the beginning of the topic and we process everything up until the present. If I stop this and then start it again, then it would, like if I leave it like this, it would again go to the beginning of the topic and then reprocess everything. If I take out this forced start, then it would only do it the first time, and then after the second time I started, then it will actually continue where it left off. So very similar or familiar practices if you are familiar with a system like Kafka. Right. Internally, the persistence in ZB is this. So the events that we saw are written to file system and in an append-only log file, and that's all there is. So it's this append-only log file that has all those events that happened, and internally the system is doing stream processing, processing those commands, generating those events, and then of course it keeps some state in certain map structures and index structures, but those can be recalculated based on the logs. The log structured persistence is also something that will be at the source of the performance that we will see later in our presentation. If you are interested more in the details behind this, we call this, oops, I'm not online, but we call this log streams, and it's in a GitHub repository that is called ZB log streams, and there you would find the Java code that is behind those append-only log streams that the ZB is managing internally. So that's the persistence. This is new. Most workflow engines would use databases. And then traditionally relational databases, and it's a very interesting question of how to implement a fully consistent workflow engine on top of a non-transactional database. And we don't have to solve that problem because we are doing the persistence based on those log streams that get replicated, as I will show in a second. And then there is no such thing as this is the state of the workflow. It's more, this is everything that's happened, and if I want to find out the state, then I can always reprocess this. And then this is the replication. So it works like this. When we start a workflow instance, the client is going to send a command to the broker. And here we have a cluster of 3 nodes. And who here in the room is familiar with or has heard the term raft protocol? A few people. So the raft protocol, who has heard Paxos? The same people. So that is a consensus and replication protocol. It solves the problem of I have data on one node and I want to have the same data on other nodes as well. So to replicate it from one node to another. This is of course a challenging problem because if we are on the network, we know that there can always be problems, there can be partitions in the network, there can be all like lost messages, duplicated messages, all sort of problems that lead to inconsistent data. And protocols like Paxos or Raft are solutions to how can I replicate data across a cluster and be consistent. So we did not invent this, but we implemented it. So in the ZB system, we have an implementation of the Raft protocol that you will find in GitHub again in ZB Raft. And this then makes sure that when the client sends a command to the broker, one of the brokers, then we can consistently replicate that data to the other nodes. To this extent, Raft has this concept of the leader. So out of those 3 brokers, it will elect one node. This is the leader. It's not in any way special. If it goes away, another node can also be elected leader. So it's not a single point of failure, but for the time being, it is the leader. And then the client can only send commands to the leader. And then the leader needs to replicate data to a quorum, including itself, to a quorum of nodes. And then data is considered to be committed. And once data is considered to be committed, ZB will send you an acknowledgement, and then it will be able internally to do the stream processing. I could talk more about those details. It's a very fascinating topic, obviously, but this is to give you a glance of how ZB internally does the persistence. So it has append-only log files or files where we can only append, and those get replicated with the Raft protocol across nodes. All right, this gives you most of the, like an overview of the ZB system. Thorben is now going to speak about a particular challenge that we have when we do microservice orchestration, and this is we want the overall orchestration to be resilient. And Thorben, back to you.
Yeah, exactly. Let's look at the topic of resilience in ZB and how it handles that. As a quick intro, resilience is the, or one definition of what resilience is that it's the ability of a system to adapt or keep working in the presence of challenges. This is a definition by Ines Sommer.
And then I guess they like, elaborated on challenges.
Yeah. And so let's see what challenges in the context of ZB are. ZB is essentially a distributed system in the sense that we have the broker and many services connecting to it. The services can run anywhere, and then it's distributed. ZB is also itself a distributed system. Like we have seen, we can have a cluster of brokers. We are not so much looking into this aspect right now, but more on the challenges that come from distribution with respect to the services that we connect with. In particular, I'd like to look at 3 cases. The first one is the case that a service is just not available. So we have started workflow instances, we have uploaded images in this example, and our thumbnailing service is not available. What happens in this case? The second example is when a service operates and is connected to ZB but runs into failures. So for example, we upload a photo that is corrupt, that is encoded in a bad way that the service cannot handle, and the service is able to tell ZB that there is failure. That's the third example, which I've called silent service failure. We will look into the case where a client is subscribed to ZB, receives tasks, and then fails without ever calling back. What does ZB do in this case? Okay, so let's start with the first example, and to explain this we have to go a little bit more to the event stream that ZB has. So the event stream is basically an ordering of events that that are either commands that are sent to ZB or the internal processing of the state machines that ZB manages. In particular, like we've seen in the demo a couple of minutes before, this is data about the workflows and the tasks that ZB manages. So for example, when a workflow gets instantiated or a task gets created or completed. So in the example of task processing, you have an event that represents the creation of a task. This event gets published to the subscribed service, and the service eventually completes the task by publishing another event to the event stream. Here it's a simplified way to show this in the sense that the service actually sends the command to do that, and then the ZB broker itself creates this completed event. So we can represent this in a kind of life cycle. So in a very simple case, we have two states, created and completed. Easy. Now, it does not work like that in real life because, for example, we can have multiple subscribers for the same type of task, and then we want to publish every task only to one of the subscribers. So we introduce, So we introduce a new state, we call it locked, and the ZB broker locks tasks for individual subscribers. So every task gets locked, and then only published to one of the subscribers.
Why would I have multiple subscribers?
To scale up your application. So let's say creating thumbnails takes extraordinarily long. Then we can just start more than one handler and maybe different machines, connect them all to ZB, and then in that way scale up our image processing. Okay, so this is how we can handle this particular scenario, because in this case, when a service is no longer subscribed, the ZB broker will simply no longer lock the tasks, and therefore also not publish them anymore. So the tasks simply remain in the created state and get not processed anymore. Let's have a quick look at how this looks like in practice. So still have our watermarker worker here running in Eclipse. And now we will kill it, so it's not creating any watermarks anymore. Going back to the application, which I think is not here. Yep, upload a new photo. Yeah, this is another beautiful house. So here it is. And as we see, no watermarking happens, so there's no watermark created here. We can see this even better in the ZB Simple Monitor. So we have the second workflow instance here. This is now the state of the watermarking, but it does not keep the state because there's no worker subscribed. Okay, this is how ZB deals with this case.
So this is like a non-event for a system. No public subscribe. If there's no subscriber, nothing happens.
F5?
Yeah.
Cool. Okay, second case. This is the case where a worker runs into an error and is able to communicate that to the ZB broker. In this case, the workflow instance should not make progress because something bad has happened. So we extend this life cycle. So the log task is pushed to the task handler. The task handler reports failure, and this basically makes the task available again. So it's created now again, it can be logged for another worker. As you may have noticed, we have now a loop in this life cycle, and where there's a loop, there's a possibility for an infinite loop. So if our worker is permanently broken, then we would have like a spinning ZB broker that does only wasteful things. In order to handle this problem, ZB has a concept of retries. So a task initially has a value of retries, and with every time a task fails, one of such retries is consumed. So eventually, if a task handler is permanently broken, the retries of a task run out, and then instead of becoming available again, the task code goes into the failed state. And in the failed state, the ZB broker will no longer lock the task and no longer make it available to workers. And now, of course, the workflow instance is stuck, and then the ZB API provides a management operation to increment the retries again to make it available again. So here the idea is that if there's a permanent problem with task execution, ZB eventually stops publishing these tasks. You can fix the problem and then make the tasks available again.
Should we demo?
Yeah, we can show this exactly. So here we have our Java, no, not this one. This is our watermarking worker. And in particular here we have the handler implementation, and instead of doing all the useful stuff, we are misbehaving this time, so we are going to throw an exception.
So this is now a badly behaving microservice that cannot complete this task, but for whatever reason throws an exception in this handler, and we can see what happens now.
Yep. So now, if an exception thrown, the CBC Client makes sure to report this failure to the broker. Let's see. Oops. Oh.
We would need to first stop the already running one, I guess.
I stopped it before.
Okay.
So let's stop this again.
I'm sure.
Oops, sorry, wrong class.
I'm sure.
Okay. This one. Okay, so in the workflow instance, we have no login, so we don't see the exception at this time, but we can again go back to the CB simple monitor, refresh this, and now we actually see that the retries have run out, and we can see in this UI that there is a problem in this particular workflow instance, and we could then probably fix it, restore the task handler, and then continue operation.
Let's maybe have a look at the log file, where you can see this happening, the retries.
So here we have a concept of incident. This is another type of event that gets created when a task runs out of retries. And here we see the fail command that is sent by the client to the broker, and the broker processing it. And this happens a couple of times because we have more than one retry by default. Yeah. Okay, let's look at the third kind of failure, which is the silent failure of the task handler. So where the task handler is not able to report that something bad has happened. In this case, we extend this lifecycle a little bit more by timing component. So if the handler never returns, then there's a time-based transition in this lifecycle that corresponds the same as if the task has failed. So the task becomes available again, can be logged, and can be published to another subscriber. And this is also what we saw in the beginning in the code, where we would define when we create the task subscription, we define a log time and a log owner. And this is basically the time that this task is reserved to this particular worker before it becomes available again. So it should be a rough estimate for how long you require to process the task. Yep. Now Daniel will give some insights on performance of CPU.
So, what I said in the beginning is what we wanted to achieve with the ZB system is to go into to a new class of performance for this kind of system. We've had workflow engines in the past for, I guess, 20, 30 years. And as we said before, most of them worked on top of databases. And we actually ended up with this stream processing model and this event-driven model because we wanted to achieve this kind of performance. And then we looked into how can I use file system very efficiently, well, with sequential reads and sequential writes. How can I get a lot of throughput with batching and asynchronous I/O, and how can I use CPUs efficiently. Well, the biggest penalty is caching and so on and so forth, and the cache hierarchy in the processes, and then out of this gradually emerged the system that was then doing stream processing. So what I'm now going to do is I'm going to do a demo of a traditional workflow engine, and this is our own. This is called Camunda. And before we do that, let's stop everything we have started here. So let's destroy all our work that we have done. And so then we should be here somewhere, yes. And also let's stop our things here in Eclipse. Yes, so now we should not have anything running here. This looks fine, yes. So what I'm going to do now is start sometimes I need to do this twice. No, this time it works on the first try. So what I'm doing here is I'm starting Camunda, which is a representative in this demo of traditional workflow engines. This one is optimized to the max. There is scientific studies that show that it's really fast. And I'm going to show you how many workflow instances per second I can start with this. So for this, it's not scientific, so the exact numbers are not going to be like, is it 10 more, is it 10 less, but it's more to give you an idea of the orders of magnitude. So this is the wrong one. What I have here is I have a Camunda BPM script. This is using REST API. The Camunda workflow engine is running on top of a relational database called Postgres, and by the REST API, this is now starting workflow instances, and it does with a couple of threads to use more cores on my computer, and we can see that now every second we log out a count of how many workflow instances are started in that second. It starts around 180, 200, 200, 230, so every second it starts around 200 workflow instances, which is a lot if it is orders in a web shop, or if it is damage claims an insurance company. So if you have 200 car accidents per second, this is enough. It's 200. Oh, now I need to put this into a spreadsheet, and I haven't prepared this. So we're going to see whether my Google Sheets is actually available offline. Oh yeah, it is. Nice. And then cover your eyes, because I haven't prepared this, so you can already see some numbers, and we need to first delete them. My little stunt is now not going to work. Okay, but so sheet is clean, and what I'm going to do is I'm going to put in the Camunda BPM numbers here, and now it's easier to understand it. So now we see it over time. So this axis is time, this is workflow instance, it started per second, and we see, as I said before, that we're starting around 200 per second. Now let's do the same thing with CB. To that effect, let's stop this, and I'm just going to start with a clean slate. So I'm going to delete my data directory in CB, and then I'm just going to run the broker once again. It's here, and I'm going to do the same thing with my ZB producer example. So now, if I want to get a lot of throughput out of CB, and I have a limited number of cores, so this computer has 2 cores. It looks like 4, but it's really 2. So it is hyper-threading. So here I'm not actually using many threads, but what we can see here is that we're like triggering those, this is not waiting. So I'm sending out the messages to the ZB broker, but I'm not waiting for the responses. In a real system, of course, I would like to wait for these responses at some point, but it's this difference between doing things like asynchronously with one thread against doing many things in a blocking way with many threads. So let's run this, and we get our numbers out of CB. So this is now the same workflow going from the first, advancing to the first step, and now we see figures like 44,000, 48,000, 42,000, 49,000, 53,000, nice. 56,000. So I'm letting this run for 30 seconds again, like before. And then I'm going to put that into the spreadsheet again, and where is the spreadsheet? It's in browser. And is it here? Yeah. And now, why am I putting this into the spreadsheet? Because sometimes data visualization gives us a better idea of what happens. So the blue line here, this is the Camunda BPMN. You cannot see it, it's more or less the horizontal line, and now this is the CB system. So, and again, sometimes it goes up a little bit more, sometimes it goes up a little bit less, but it is, what I want to show with this, it's an order of magnitude different from what was possible before. So before CB, you get the blue line, now we get the red line. And why? Because this is a completely re-architectured system that literally works completely different from any workflow engine that has been built before. And to compare that a little bit, I'm going to show you the data directory. So I'm now stopping the ZB. And so I'm here in this ZB installation. And when we say, so this has now produced 1.4 gigabyte of data, the 30 seconds that I have been running it. So this is the big data system. That's also why I'm going to talk a little bit about scalability and multiple nodes and multiple workers. So this is 1.4 gigabytes of data. What I'm now, that it produced, what I'm now going to do is I'm going to use the Apache Kafka system, which is of course different from ZB. So this is now not comparing ZB against Kafka, it's more to show you that with the ZB system we get, in terms of the performance, we get into the same kind of space where those messaging systems are. So I'm going to produce more or less, it's hard, more or less the same amount of data with the Kafka system. And to achieve that, let me see, I need to start the Zookeeper, this one. Yes, I'm starting the Kafka. Here it comes. And we need to create a topic. And what I'm doing here is I'm creating a topic with a replication factor of 1 and a partition and 1 partition. In ZB we have the same. In ZB we have a concept of topics and partitions, and it's very much the same. So if you want to scale, we're going to talk about that, then you need multiple partitions on your topic. But here in the ZB I used 1 partition, and in the Kafka I'm going to use 1 partition as well. So it already exists, but then we don't need to create it. Or let's maybe create, because let's name it default 2. Apparently I reversed before. So now we have this other partition, and then I now have a simple, very simple Kafka producer, and then we need to go to the topic default 2, and also what we see here, the producer is doing send in a loop as fast as possible, and also not, like this gives you back a future in Kafka, and we're not waiting for that future to complete, so we're just trying to pump as much data into the system as possible, and as fast as possible, which is the same that we did in ZB. And what we're publishing here is basically messages that are 512 bytes in size. Why 512? Because I want to end up with similar amount of data in my file system later. So when I run this in Kafka, then we will see how fast I can go. So this is now events published to Kafka. I see I go, I start at 50,000, we go to 100,000, 140,000, we go to 200,000, let it run for 30 seconds again. 250,000, 80,000, yeah. And now, this is the number of events I can publish into the Kafka system. per second on this computer with this particular configuration and so on and so forth. I have a different tab here. So let's do this right here. So I'm going to put the Kafka in here. And now, so this is the number of events that we have published into the Kafka system over time. And when we started workflow instances in ZB, so we had these numbers. So those are lower, of course, 40,000. But whenever I start a workflow instance in ZB, that's actually internally 6 events. So I need to multiply those numbers by 6 to compare kind of events written per second. There's a different system, so we don't compare the like events ingested into the Kafka. But so if I multiply this by 6, because it's 6 events written, I now need to do some spreadsheet magic. You can just observe how I do this. So this is bad. No, I need to put it here, and then we need to delete this. I could have prepared this better. I had at some point F7 times 6, still 0. Infinitely slower. So then this is what I wanted to show. So this is now not about saying one system is slower or faster than the other. It is about showing you in terms of how many events ZB has written down per second for starting all those workflow instances. That's the number of workflow instances we have started times 6, because each workflow instance is 6 events. Then we are in the same order of magnitude. We will see now that the Kafka system has produced Kafka logs has produced 2 gigabytes of data, so a little bit more. I should probably not have published 512 bytes, but somewhere around 300 bytes. So you see, it's not exact science, but what I want to convey is that with the ZB system, we go into a class of performance and into a class of throughput that before was only possible to do with messaging, and now you can do that with workflow as well. And this is what I wanted to convey with that. So going back to the slides, I have some backup slides in case the demo doesn't work. So how does ZB achieve that? I will not go into the details, but we'll do a lot of low-level optimizations in here. So as I said before, we go into how can we use file system efficiently? How can we do I/O efficiently? Well, by batching. So if you do a write to file system, it doesn't matter if you write 2 bytes or 500 bytes. It will be more or less the same speed. This is like 2 people going into an elevator versus 5 people going into an elevator. They will all arrive at the 5th floor at the same time. So there's constant costs around I/O operation, and batching helps us there. Then the linear access patterns. So this data goes in a file and you can read it linearly, you can write it linearly. This is how hardware is designed to be used. We have internally quite interesting compact data structures. So Thorben talked about the state machines. Each task is created and then logged and then completed. So this is a state machine. We have a very efficient homegrown map data structure in the ZB that is very cache efficient and is very fast to access. And things like that. If you are interested in low-level garbage-free coding in Java, come to me after the talk, then we can talk about those things. But yeah, so this is one thing. This is how we can get a lot of throughput on a very modest system like this. So it, as I said, it tells us that it has 4 cores while it has only 2, and it has 8 gigabytes of memory, and it's an Intel Core i5. So that's modest. So we can get a lot of throughput out of modest system like that. And then if we have more than one computer, then of course we can scale it. So the ZB works as a cluster, and then you can scale it up and down. That's kind of the idea. And we are looking into orchestration, like container orchestration frameworks. So for example, there is a project that is called the ZB operator. This is a plugin into Kubernetes, and that allows you to easily manage a cluster of CB servers on top of Kubernetes. Who knows Kubernetes in here? Who's using it in production? We are. Yeah, that's cool. So it gets adopted more and more, and of course it's the perfect match for running distributed systems like this. Yeah, that's to give you some overview of performance. And now to round this off, in the beginning we said that the vision around workflow is about providing a solution that gives you the way to do the orchestration and the distribution of work, the resilience that Thorben talked about before. We have the performance, and now the last aspect is the visibility into flows, and Thorben is going to explain us that.
Yeah. So let's look a little bit deeper into the principles, how you would actually implement this kind of introspection that we have seen in the demo also. So there's two kinds of introspection that we can answer with ZB and the workflow concept. So one is more the technical responsibility for workflows. So do all workflows that we have in our large system, do they run such that they produce something in the end and do not fail on the way? And then there's more the business aspect to all of this. Do our workflows produce something of business value, and do our software systems in the end produce that the product that we thought of initially, and are they efficient? And we'll look at both kinds of questions here and how we can solve this with workflow introspection. So on the one hand, in the microservice architecture, we have service monitoring of individual services. This is very helpful for technical monitoring of the services. And then there's workflow monitoring, which is kind of complementary to that. So with workflow monitoring, we can answer questions like, are there tasks piling up because there's some problem in our system, or somewhere manual intervention required to repair something before the workflow can continue. Again, all of this is based on the event stream of ZB. Like we have seen, we can subscribe to this event stream, and how we would build an application like the ZB Simple Monitor that actually allows us to visually understand what's going on in ZB is by interpreting the events that we see on the stream. So for example, whenever we see that tasks are created, we can annotate this in the BPMN model. And here's also kind of the value of BPMN as a visual representation of workflows, because we can show this to technical as well as business users and then annotate it and create a rich presentation of the workflow state. Similarly, we can interpret other types of events. So here, for example, the failure, then we would annotate this at the model as well, and then, for example, the operator can see that something's wrong. We've seen this in the demo before. At Camunda, like Daniel showed that, or compared ZB to Camunda BPM, this is like Daniel said, a workflow engine that we have developed over several years, a transactional workflow engine, and there we have a product that's called Camunda Cockpit, which implements exactly this idea, which is a rich interface for operators where they can see the workflow models and the state, single workflow instance, also aggregated states, and immediately see where there are problems in the workflows. Let's touch the business side of things. So where we want to have a more high-level view of if the workflows are doing the right thing. So here we have extended this watermarking process a little bit by a service that is able to detect if the content is appropriate for our system. And if it is, then it takes this branch where it continues with watermarking and thumbnailing. If it's not, then it deletes the photo. And for example, from a business side, we could define KPIs based on the workflow. So, for example, we could say that our workflow system, or the implemented workflow is good if there are more than 80% of images that are appropriate and we do not reject everything. So then it's a good system in a sense. And we could define this KPI based on the workflow because we have different outcomes in our workflow. And then again, we can use the ZB event stream to basically see how many workflow instances go to one of the branches, and then calculate this KPI and then probably notify someone if the KPI gets violated.
It's a simple stream processing on top of the event stream, as Thorben showed before. So whenever we reach here, we do +1 on one counter, and whenever we reach here, we do +1 on another counter.
Yeah,
super simple.
Exactly. Again, Camunda has an application built on top of Camunda BPM that is called Camunda Optimize that does exactly these kind of things. So here we see a view that is called the heat map that is a nice intuitive visualization of how instances of workflows go through a workflow for large numbers so that you do not have to look at individual instances. And you can also then, of course, filter by certain dates and so on, whatever interests you. And show these examples because the principle is the same in a system like Camunda BPM and ZB. So while ZB is not still a young project and there are not such tools yet, it is certainly possible and we are willing to build these tools and then really create a great workflow platform. This concludes our talk and now we could have a Q&A session.
Thank you very much for the great presentation. This beats the Champions League any day.
So when does the game start? At 8:45 usually, or?
Are people already rushing out?
Well, we have one thing that should make them stay. So we have, if your T-shirt size is L
Or M.
and you are among the 10 first people who ask a question, you get a CB T-shirt then. And Daya is going to throw them into the...
I will run around with a microphone to catch what you are actually asking. Please go ahead.
So do you have a configuration for the message delivery? Like Kafka, for example, has delivery only once, at least once. So do you have such a mechanism?
This is your expertise.
Yeah, with ZB you have at least once delivery for the tasks that are published to the handlers. So you can have, the handler must be able to deal with a situation where a task gets published more than once.
And it's not configurable by the user?
No, in the current state it's this way.
So there's three things that make sense, at least once, at most once, and exactly once. So at most once means that if I'm in the workflow, I go to the task, it's going to be given to a worker or a handler as long as necessary until the handler signals completion. So that's why it's at most not once, at least once. If it were at most once, then we would give it to the handler, and then if we never hear back, go to the next step. Currently, I'm not aware of any situations where that would make sense in the context of workflow, but it could very well be that we don't know those situations yet because we are also very in the beginning with this system, and if that situation arises, then this is something that could be easily, based on the state machine, could be made configurable. So we hand it out to a worker once, and if he never hears back, then after the timeout, we go to the next step. That would then be at most once. Yeah, that would be making it configurable. So do we have a T-shirt for? Yeah.
Does she want to come after them?
As you want, I can throw them.
Yeah, so Daya is the girl sitting in the right, or from our perspective, in the right corner, and if you want to have a T-shirt for the question, you can approach her.
So, about the consumption, so you said that once you do force start, all the consumers will start consuming from the first first index. Which means that, so do you also have a concept of consumer groups here in ZB?
That's a very interesting topic for us. In the current score, we actually are currently developing this field. So for everyone who doesn't know Kafka so well, a consumer group is basically that you have an event consumer and you want to scale this consumer. So you can subscribe to one topic. This topic maybe has many partitions. And these events should not all go to one single client application, but you want to have many of those so that you can scale up the event processing. And this is also very interesting feature for ZB. In the very first step, we are building it in a way that only a single client application can be subscribed, but we definitely think about this topic and want to have it eventually in ZB as well, that you can have a group of consumers where each consumer gets events from different partitions, and it's still guaranteed that every event is seen by one of the consumers.
And for to extend on that, there's two types of consumers. There's the task consumers that do the actual work in the steps of the workflow. And there's the event consumers that put in the audit log the history of everything that has happened, and then maybe calculate some counters on top of it, or do the visualizations. Now, the workers that do the actual work, and task consumers, the workers that do the actual work in the workflows, you can scale them currently. The other one, in the current implementation you can't, but in the future, as Thorben said, that shall be possible as well. But right now we are focusing on other aspects of the system. Yeah.
No.
I think there's a follow-up question.
Follow-up
question.
This makes things complicated.
How does ZB maintain the broker configurations? So how does it know that which partition this message goes to? Does it internally use scope data systems, or does it use some external tools?
Yeah, so we have a cluster. ZB does not rely on any external systems, so it doesn't rely on databases, it also doesn't rely on an external consensus system like Zookeeper. It does all of this internally by two concepts. One is the cluster membership protocol. We haven't talked about this. This is Gossip. Who has heard of Gossip? Everybody who has been running Cassandra, or like maybe Consul or something like that. So internally it implements Gossip to know who's there. And then on that level it can also detect if nodes go away and so on and so forth. So it implements the Gossip protocol for the membership. And then on top of that, for the data replication and then the leader election, it implements the RAF protocol. And then you have to think, and this is a little bit complex, you have to wrap your head around it. So you have topics, and those topics are partitioned, so to shard them, basically. And then each partition or each shard is going to have multiple copies. Those are the replicas. So when I have a cluster like this, then let's assume I have one topic and 3 partitions. Then, for example, this broker would be leader for partition 1, and this one would be leader for partition 2, and this one would be leader for partition 3, for example. But this one, who is leader for partition 1, would potentially also be follower for partition 2 and 3. So it can be leader for one fraction of the data, and then follower or replica for another partition of the data. Now the client, when it sends a command, we had that here. Skip back, way back. We had it here. So when the client sends a command, it always needs to find the leader. We have this concept of the cluster topology that is distributed through Gossip. So through Gossip, these nodes will talk about, hey, I'm leader for partition 1, I'm follower for partition 2, and so on and so forth. And then, with the timeout, regularly the client is going to fetch the topology from one of the nodes. But then, of course, that topology isn't necessarily exact, because it can be outdated, it can change if there is a leader change, if the Gossip will not be really consistent, and so on. So it can happen that the client sends a command to one node that is not leader for the particular partition we're talking about. And then that node is going to send back an error, so hey, not for me, please go somewhere else. And then the client needs to find the leader. So that it will probe different nodes around the cluster until it finds it. That's more, I hope that was an answer to your question. I think the microphone is...
Just wondering, the next two I have in my head.
What were the reasons that you decided to build your own log-like storage engine and clustering, of course, instead of having the burden to have the dependency on Kafka and Zookeeper?
2 reasons. One is performance, so we want to be really, really fast. And if we have, so we do, comparing to Kafka, we do a lot more in the broker than the Kafka. Kafka needs to store it, it needs to replicate it, it needs to maybe do the time to live and compaction and so on, and that is a workload that you have on the node. The ZB needs to do a lot of stream processing, and to do this really, really fast, it really helps if the data is available on file system on that node. So we can process events at a very, very, very fast rate on a single node. So one aspect is performance, now at least for the log storage. Then the other reason is that we want this to be a system that is easy to run for our users. So if you want to use ZB, you start it up and then it's there. And we didn't want it to be in a way that, okay, first you start Zookeeper, then you start Kafka, then you start maybe like Cache, and then you start ZB. That would work if you are already running all those systems in your company anyway, then it may even in certain situations be easier to do that. But if you're not running those systems, then it would build on top, on top, on top, on top. And this is, to a certain extent, what has happened in the past. So if you look at heavyweight, black box, BPMN suites, like by the big vendors, for example, they build on top of the IBM middleware stack, or they build on top of the Oracle middleware stack. So you have the database, you have the cache, you have the messaging system, and on top of that builds the workflow engine. And we wanted to have a system that's really lightweight, and then not built on top of, well, then in this case, the Silicon Valley middleware stack, which would then be Zookeeper, Kafka, and maybe, I don't know, Redis. So that was the main reason. Yeah.
Thank
you. Yep. You show us the command line tools to deploy the workflow definitions. Are there also ways to automate that, either via build tools like Maven, Gradle, or even plugins for common CI systems like Jenkins?
Not at the moment, because it's very in the beginning of things, but that's actually a really nice idea. So, well, there's the Java client, and with the Java client, I could implement a Maven plugin. That's probably going to be a small wrapper around it. And then as part of my Maven build, I could install, or we could have a Jenkins plugin. We currently don't have that, but that would be really nice.
Does it exist for Commando? Because I worked in a project where Commando was involved. Does Commando already have that kind of support?
Bernd, do you know of, like, we don't have it in the core, but Bernd, do you know of any like community project, or not at the moment? No. But this is something that would be really nice to do. What is there in terms of integration? We don't have internet currently, but what is there in terms of integration is anybody out of the Java people using Spring Boot? Or Spring, yeah. So there is an integration into the Spring framework, and then also Spring Boot. And with this, you can have the client starting immediately and hooking into Spring, and then it will find BPMN files in your class path and things like that. So that can be maybe also an alternative.
Do you have perhaps plans for support for other languages? Like you told us that it does only work with Java and Golang, for example, C++, or other bad systems.
There's currently we're working on the Java and the Golang, and right now the system we're focusing to really get it production ready, which is a little bit down the road, so there's work to do. So right now we're not broadening the scope. Once we are production ready, then we're going to broaden the scope in terms of the client, and then the Golang client is going to open up a space of different languages, because with the Golang you can have the foreign function interface, and then, for example, you can build a Node.js wrapper around it that embeds the Golang client, and then basically in the Node.js client I can then pass in a function that gets called when a particular task in the workflow gets reached. So to have an automatic Node.js wrapper around it. We have prototyped that, Felix has built that, but this is not something we're pursuing actively right now because we need to focus on getting the system ready. But it's something that is on the roadmap once we have reached this next milestone. And then it will be Node.js, and Python, that's going to open up on top of the Golang client. And I guess in C or C++, if you want to have the full performance, then it would be good to write a client in that language. What is also really interesting is C#, because quite a few people use C# in their projects. It's an interesting language, it has a big community. This is also something that we want to target. Which language would you like to see? Personally?
C# would be interesting.
C#.
Also C++.
Yeah.
Okay, so the performance demo you showed us, I think it was with a single broker, is that right?
Yes.
So can you say a bit about how the performance looks like when you have the Raft protocol in place compared to Kafka?
We're not that far yet. We don't have those numbers yet, so I don't want to give you any. We have used it with the replication, and of course replication comes at a certain cost. So if I don't do replication as I did it here, I'm of course faster than if I do the replication. The replication is implemented with the same principles. So it is non-blocking and streaming, and that means when data comes in, it naturally kind of flows through the system. So it goes to the file system, and then it gets pushed out to the followers. But we don't push and then wait for X, but it pushes and then you get the X, and if you don't get them, you need to go back and then push the same data again. So it's non-blocking and streaming, and it's designed in the sense that it uses the hardware resources to their capacity. Now, of course, we cannot go beyond that capacity, but we are honestly not that far ahead yet that we have demos like this with a cluster of nodes against Kafka again with a cluster of nodes. Yes.
My question is in correlation with Camunda BPM workflow engine. So if you have the Camunda already in production, does it make sense to extract the high-load processes to the ZBO? What's your suggestion in that case? And in the roadmap of the ZBO, is there some plans to be part of the Camunda, so I can choose a modeler like execute this process on that part?
Yeah. So this is our goal towards the end of 2018, beginning of 2019, that at some point, depending on how fast we make progress with the ZB project, at some point we can replace it. Well, not replace it, but at some point users could choose in the Camunda product between one workflow engine or the other. If you are on the Camunda BPM and you don't have the super high volume and scalable and resilience requirements, then I would very much recommend to stay with that. It's just like, I don't know, like 15 years ago we thought that NoSQL databases would eat up SQL databases, and here we are and they're still there. Because there is a very nice use case for them, and there's a sweet spot for SQL databases, and this is similar. So Camunda that you're using is a nice transactional workflow engine that solves a particular problem in a really nice way, and the ZB is now coming to solve this problem as well, but also other problems. And as long as you don't hit any bottlenecks, or as long as you don't hit any roadblocks, you should stay with the system you currently have, I would say.
So thanks for the cool stuff you do. Could you explain the reasoning behind having publish subscribe to connect to external systems instead of actively calling them? And how would I implement it if I would like to make it this way, like in the cloud functions today?
You maybe have a REST API you want to call it, right? Yeah. Well, one builds on top of the other. So the publish subscribe is kind of the low-level layer, and then as a user of ZB, I can then choose. I can either embed the client into my microservices directly, and then do the publish subscribe protocol. Publish subscribe protocol has some nice properties. One property is that it gives a lot of control to the subscriber. So as Thorben showed, when the subscriber is not subscribed, nothing happens. It's a non-event. If the workflow engine calls the other side. If the other side is not there, then we cannot reach it. So yeah, if it's always there, it's not a problem. That's one thing. So the subscriber controls when it wants to process tasks. The other thing is the publish subscribe protocol is really easy for the subscriber to control the rate at which it publishes tasks, processes tasks. We haven't gone into those details now, but embedded into this publish subscribe protocol is a back pressure protocol. For those who are not familiar with back pressure, this is a principle of, so I'm a consumer, I want to do work, and I can do this work at a particular rate. If I'm not fast enough, I need to push back on the producer assigning me the work to slow down. Inside this task, publish subscribe protocol that is in ZB is embedded a back pressure protocol. So if you have really fast workers, they can process events at a very high rate, and if you have slower workers, then they will process tasks at a slower rate. But this all works automatically, so it's not something that we need to tune or that we need to configure, it's just inherently part of the protocol. So that's the second advantage of the publish subscribe. So I control when, I control the rate, and the third advantage is that the broker doesn't need to know the location of the subscriber, so I don't need to know how to reach this guy. It will call me, it will subscribe to me, and this just makes quite a few problems that we usually have around the service discovery. Who should we call? Are they there? At which rate should we call them? So this just makes all those problems go away because the interaction is inverted. But now, still, if you want to do the just call REST API because you have it and it's nice and works perfectly, then you can build on top of that. So you can build one general purpose worker that is configurable, that subscribes to all the tasks, and then just calls REST APIs. So I get a task, I look at the payload, it says call this endpoint, I call the endpoint, I get the data back, and I complete the task. And this would be a module that down the road that could be out of the box, so a generic REST service worker that you can configure and that can call REST APIs. The same is true for all kinds of other generic workers that you can provide. Call REST APIs, send emails, archive files to S3, whatever, like stuff that is just reusable and composable. Yeah.
Still more questions. Cool.
I mean, this is 15 minutes into the game almost.
I'll be quick. One of the advantages of traditional workflow engines like Camunda is the ability to reason about things like compensating actions, semantic undo operations. We haven't talked about that within the context of ZB, but in an environment where you have at least once delivery, and you have triggered a compensating action from your first parallel instance, how do you cope with undoing state in your second parallel instance?
Let's try to so you have parallel. With parallel you probably mean, oops.
No, I don't mean within the DSL description. I mean incidental parallelism due to, for instance, a network partition.
And a network partition in the sense that we have different workers in different partitions, or?
Accidental network partition has caused redelivery due to a timeout. So you have two workers processing the same request.
What we talked about before.
One of them has triggered a compensating action because it is completed first, and the other one completes.
Okay, I'll try to rephrase the question and to make sure that I fully understand it.
Sure.
So we have a situation where we have a worker on this task, and it gets assigned a task. It gets assigned a task, and then it cannot complete it. It works on it, it cannot complete it because it's now partitioned out into a different network partition and cannot reach the broker anymore. Is this the situation? And then, of course, the timeout occurs that Thorben was talking about. So now a timeout occurs, and this task now gets assigned to another worker. Now, in this situation, the first worker will not be able to complete this task. So it's going to try to send a complete request that we have seen in the Java code. So in Java code we have seen all this code in the handler, and then at the bottom it said complete. So it will now execute this, and then it will not be able to complete this. Now, in this case, this is going to throw an exception, and then locally I need to undo whatever I have done. Now, problem can of course be, well, there's many problems. Problem can of course be I'm not, like, I'm getting killed before I can handle this exception. These kind of things. And to this, there is no out-of-the-box, there's no out-of-the-box answer to this. So this is something that, in a domain-specific way, we would need to handle. In general, those workers need to be idempotent, so they need to be able to cope with the redelivery of messages. But there is, of course, situations where the worker itself cannot get back to the broker cluster, and then it locally needs to undo its things, and then it's an interesting situation where you are killed before you can do that. What some people do in that situation is that locally they have a transaction. So let's assume this worker writes to database. So what it would do is it would open a transaction, it would do its work, and then it will send a message to the broker to complete the task. And if that is successful, then it will locally commit its transaction. If it's not successful, then it will not commit this transaction locally. It doesn't have to, because the broker makes sure, or the CB in this case makes sure, that this task is completed as long as, as many times as necessary until we have this signal back. So that would be one possible way to deal with that, I guess. But maybe we can take it offline later. Because
I think maybe it's worth taking it offline, but I was thinking more in terms of the advantage of a workflow is you can have a multi-stage compensating fact flow. If you've triggered that multi-stage compensation flow, and then your parallel worker also tries to complete because the partition stops, then you've already triggered, but you may have incidental state left. I don't know, maybe it's better to take offline.
I think we should, yeah.
So I believe there will still be questions. You stick around for some further beer, hopefully, and maybe no pizza left. But stick around for beer and some discussion. Thank you very much. This was a great presentation.